let's solve a couple more problems involving secant and tangent and their powers. The first one is secant cubed of x dx. Now this one's kind of tricky because we're going to have to use an integration by parts here. Fun, right? So what we're going to do is we're going to separate this into its pieces. We're going to say that's actually equal to secant x and secant squared x dx. So what I'm going to do is I'm going to say, okay, well, secant squared x dx, that is the derivative of the tangent function. So if I say, all right, u is whatever, and dv secant squared x dx, that means that v will be tangent of x. So what's left over is secant of x, so du secant x tangent x dx. So I can now use integration by parts, which hopefully you feel more comfortable with by now. I can use integration by parts to solve this. All right, well then remember the format for that is this integral is equal to uv, so secant x tangent x, minus the integral of v du. So that's secant x tangent squared x dx. So secant x tangent squared x dx. So then I've got some sort of odd power and some sort of even power of tangent. So when I have something like that, what I would want to do is I want to convert these tangents back to secants. So I have secant x tangent x minus integral secant x secant squared x minus 1 dx. So remember the tangent squared x is secant squared x minus 1. That will separate this into further integrals. Secant of x tangent of x minus integral of secant cubed x dx plus integral of secant x dx. Oh, no, right, so now we have this integral equals this. Well, this is on the same side as that. So those are on the same side. Now they don't cancel, right, because they don't have the same sign. So what we have to do is we have to actually add this over. So if I add that over, now what I get is I get that 2 times the integral I'm trying to solve for is this 2 times the integral I'm trying to solve for. So instead of 2 times the integral, I just do 1/2. I divide everything by 2. And you may not remember, but the sort of, you can look that up in a table, integral of secant of x dx. We'll get there. Is the natural log of secant x plus tangent x. And so that's how you solve that type of problem. Secant cubed x dx is actually one of the harder integrals because it involves integration by parts. It involves that sort of add back methodology in integration by parts. It also requires you to use the trigonometric identities and stuff. It is a complicated integral for something that looks like it shouldn't be that difficult, but it sure is. Okay, so now that we've done that, let's go over here. Tangent 4th x or secant 6th x dx. Now, in this case, we now have a secant in the denominator, and we haven't encountered that. We don't have to deal with that. Now, we can try to do the methodologies we did before. I can split tangent into sort of like secant squared minus 1 and then another secant squared minus 1, and then I could multiply it out, and then I could split the numerators, and then I could do that, and that would all be possible. It's all perfectly fine and okay to do. It's not exactly what I would recommend instead. So what I would say is actually let's convert this to sines and cosines. So tangent is sine over cosine, so tangent to the fourth is sine to the fourth over cosine to the fourth. And secant is 1 over cosine, but it was in the denominator, so it's 1 over cosine. So that double flip brings cosine to the numerator here. So if I have cosine to the fourth and cosine to the sixth, those have a cancellation property. So now we have sine to the fourth x, cosine squared x dx. Now the way you want to solve this is then by using the power reduction formulas. We would say, okay, we do that, and so, and hopefully you watch the other video that we do on the trigonometric integrals, because we do something pretty much exactly like that, and you can walk through. Now I am going to, because that video exists, I recommend you go look at that. It should just be a couple back in the queue, but if you want to see something else that's a little something that the way I would do it, and this isn't necessarily the right way to do it, but a little trick that I might employ is I might say, okay, well, I know that that's going to be 1/8. Right, because I pull out the 2 in the denominator 3 times, twice for this one, once for this, so I get 1/8. Now what I notice is this. I notice this piece. That's a difference of squares. That's a 1 minus something and a 1 plus something. So I actually get 1/8. One minus cosine 2x times 1 minus cosine squared 2x. So why is that helpful? Well, that's helpful because this is actually sine squared. So then I get 1/8, 1 minus cosine 2x, sine squared 2x dx. At this point, I can then use the formulas again if I wanted to. But the issue you would run into, I believe, if you were to do that, you would have to use the angle addition identities. So if I were to run this again using this formula here, I'd end up with 1/16 integral 1 minus cosine 2x, or the sum to product, not angle addition, 1 minus cosine 4x dx. So this presents an issue. The reason why is because then you end up with 1/16 integral of 1 minus cosine 4x minus cosine 2x plus cosine 2x cosine 4x dx. Right, so that's an issue there that you run into. There's probably ways to mitigate that. But you'd use the sum to product formulas there, which we're going to cover, and you could use the sum to product to convert that into, or actually product to sum rather. You would take that and you would convert it into 2 more things that you could then multiply, because these come out directly as, so that's going to be, x minus 1/4 sine 4x minus 1/2 sine 2x So I'm going to wait and deal with that. But the idea here ultimately is that you can use converting from sines to cosines, and then you can use power. You can use by converting to sines and cosines, you can use those power formulas that we had for sine and cosine to try to get it. And again, this is going to come up in our next piece, and we'll cover how to solve those types of problems.